Hello everyone, welcome to the webinar series with the IEEE Industrial Electronics Society. Thank you for joining. Today's topic is multi-objective, multi-constraint optimization of electrical machines. And it's being presented by Shafiq Nateg from Polestar in Sweden and Yves Thiollier from PowerSys in France. First, we have some housekeeping announcement. Today's webinar will be live, it's being recorded, and it will be placed on our IES Resource Center within the next few weeks. We invite you to use the question function on your panel to ask any questions you may have regarding the content or any broadcast-related issues. Questions regarding content will be answered verbally at the end of the webinar. I will now welcome Shafiq Nateg and Yves Thiollier so they can begin their presentation. We hope you enjoy the webinar.
Okay, thank you. Thank you, Cécile, for the nice introduction. Thank you for joining. So indeed, we are going to talk about multi-objective and multi-constraint optimization. Here are the contents of the presentation. First, we will introduce ourselves and our companies. Then we'll have two parts. Part one is about narrowing the range of the global optimization using multi-objective and multi-constraint optimization. I will do this part, and the second part will be done by Shafiq, and it's more about topological optimization, which is a bit different type of optimization. Finally, we will have the Q&A session and the wrap-up. Let's start with the company and presenter introduction. So I am Yves Thiollier from PowerSys. I'm in charge of the GMAC technical support since 2007. And GMAC software has been developed by GSOL company in Japan. This is my company, so PowerSys. We distribute the GMAC software. And of course, we are in charge of support, integration, training, consulting, and also HPC calculation with our latest tool, the PowerSys Cloud System. So Shafiq, maybe you can introduce yourself.
Yes, thank you very much, Yves, for a very good introduction. Yes, my name is Shafiq Nateg. Today, I work in a company called Polestar. We produce electric cars. A little bit about my background. I have a PhD in electrical machine design from KTH Royal Institute of Technology in Stockholm, Sweden. I was a visiting scholar in US for some months, and then I started working in Rolls-Royce Marine. I was designing electrical machines there for marine applications. After that, I work in railway business, the same job, designing electrical machines for Bombardier. And then I worked as a senior engineer in e-mobility department in ABB in Sweden, doing the same job. After that, I moved to Volvo Cars in Gothenburg in Sweden. And I was a principal engineer working with electrical machine design and analysis. And now I'm a senior principal engineer working mostly with electrical machine design still. I hold also a position as Secretary of Electrical Machines Technical Committee in IES IEEE Society, and also I'm the Associate Editor of IEEE Transaction on Industrial Electronics. Thank you very much. I think we have one slide also, next one about the Polestar, yeah. So the company I'm presenting today was basically made by Volvo Cars some years ago, but now we are in a kind of transition to be a little bit separate. Today we are producing tens of thousands of cars per year, and by end of 2025 we are gonna increase it to several 100,000 of the car, close to 300,000. The picture on the right on the top was our first car, which was the Polestar 1, and that's an hybrid car. But after that, the whole company strategic decision was to go towards electric cars, full electric cars. And the most sold car that we have today is the one below the golden one, which is Polestar 2 on the right bottom. And beside that, you will see the SUV, which is Polestar 3, which will be released this year. And in end of 2024, we will have Polestar 5, which is called Precept, which will be our major release of the cars. Yeah, that was about Polestar.
Yeah, thank you. So let's move on the part one about global design search for multi-objective, multi-constraint optimization, and the corresponding issue by narrowing down the design space. Here is the contents of the part two. First, I will give you an overview of the model and of the objective function and constraint. Then we will see how we can narrow down the range of all the variables and the constraint using purely FEA calculation. And then in the next paragraph, we'll try to compare and to check how it is possible to use this narrowing down also with other different calculation methods like equivalent circuit or experimental design. And finally, we will check the calculation cost and compare the calculation cost at the end, a brief summary. Okay, so you may know that now for electrical motor, we need to be to have very high performance electrical machine. And for that, it needs to satisfy many requests. So we are going to use some multi-objective and multi-constraint optimization. And we have what we call the genetic algorithm that will help us for that. It will also be helpful because we also need to make this for multi-point, so different working point, different speed, different torque. The issue of those genetic algorithm is that the calculation amount is not neglectable. It's significantly rising up when you've got many constraints. So one solution would be to make some pre-processing by narrowing down and to reduce the range of those constraints. But of course, this will include some risk, like personal judgment, like approximation due to the calculation techniques. So we'll review a bit those risks in this presentation and see how narrowing down could be performed correctly. So we will see that through an examples, permanent magnet motor optimization. That will be our example. So let me show you this motor examples. Here is the motor. Here is the motor model. So we will make it simple. In that case, only one magnet. And here is all the dimensions we are going to optimize. So I'm not going to detail everything, but here you can see slot opening, rotor, radius of the stator. Then you can see the magnet width, and also here some space between the magnet and the rotor border. And so here you've got the list of all the design variables. So those one are a very classical one, and that's based on classical motor design. And here you can also see the maximum range that could be used in that motor. And we will see how we can narrowing down those range here. Let me now introduce the objective function. So still here, it's a kind of classical design for motor. So we are going to maximize average torque, minimize torque ripple. So that's maybe to reduce noise and vibration. And of course, we will try to minimize the loss so that we will increase the efficiency. Regarding the constraint conditions, in order to make it feasible, we also have something to apply here, like voltage limit. So we are going to check back EMF voltage. We are going to try to check the stress also in order to prevent damage from centrifugal force. Of course, we will also check the volume because we've got some constraint here. And in order to reuse the motor, also many times we will try to check the demagnetization ratio in order to prevent demagnetization, especially at high speed, because we are doing that at 2 different points, one at low speed and one at high speed. Resulting of this 6 objective function and 11 constraint, you've got a table showing everything there. So you can see that some constraints are just happening at the high speed, like, as I said, the magnetization ratio, because it's critical at this speed. You can see that some are objective functions, some also are constraints. So that's also some classical design, and objective function and constraint. Okay, let me show you briefly how it is working. So in the JMAG, so here is our model. So you can see it now. And you can see that under this model, I have many studies, not many, but okay, some studies. And all those studies are corresponding to some checking. So here we've got the low speed, high speed. Here, for example, we've got the back EMF. So for example, if I edit the circuit, you can see that now I have a current sources with some 0 current here, so no current. And I'm going to check voltage here. So that's a very classical voltage check. And you can see also that we have here some response graph data checking the back EMF, so checking the voltage. We've got one other study, which is for stress. So here now you can see that only only rotor is applied. Here we are also making some response graph data about stress, max stress. So if you check here, edit, we are checking stress and maximum stress. And that's all our studies, and that's very easy to create those studies, because you can reuse the previous one and change the speed and the current and etc. You can create all your response data, and you can create this analysis group. So you see that in my group, I have all the previous study I have shown. And in the response graph data, all response graph data coming from all studies are collected here. So you can see this stress, I show you back EMF, and of course we've got the same one I did not show you, but you got average torque for high speed, etc. And so on this group, you can directly go to the optimization and place your optimization function directly here. Here first, of course, the constraint with all the range, okay, and then comes the objective function. So you can just place there the objective function based on the expression of the response and minimize and etc. So here is the model. Here is what we are going to play with now in the slide. So let me be back to full screen. So now I presented you the model. I've shown you how I implemented that under JMAG. Let me show you the results. So this results is the one stage. So it means only one optimization will be run with a population of 200 cases for one generation and 20 generation. Okay, so here is, you can see the number of feasible solutions. They are highlighted in red, okay? And it means 200 multiplied by 20, so 4,000 cases, 4,000 calculation to be run. So here also in JMAG, you can also access to all the response graph data and create directly your graph by generating. So for example, you could have all the response graphs data that are here. So for example, iron loss and torque, average torque, high speed, for example. And here you can also you can generate very easily that kind of graph. So now the question is how how to reduce this amount of calculation by getting more solution in the feasible area, and also updating more quicker the Pareto front. So what is proposed here is to make a two-stage optimization. So it means that we will just run one stage, okay, check the variables and check the range of the variable and check how they evolve, and use this new range into a second stage. So it means restarting the optimization. And so we will see that at the end of the first stage, so first stage is in fact 5 generation. So the first stage is five generation of the optimization, and you can see that for these particular variables, so that's the, if you remember, the distance between the magnet and the rotor border, you can see that these variables, you can see that the range is going down. And you can imagine that you could do that for all variables, okay? And it means that at the end of the first stage now, so you see here it's maybe 15, here I remember it's 2. If you go back to here, we are for LM 2 and 15, okay? So we use the full range, but now for the second stage optimization, we will maybe go to 8, from 2 to 8, and that will be our second stage of optimization. And at the end of this second stage, still 200 individual, 200 cases, 200 calculation per generation. And you can see that we've got much more calculation close to the feasible area, and we also update more quicker the Pareto front. The results are not spread away like this, okay? They are really near the Pareto front and really near the feasible solution. We have less solution, but it's also because we have less cases. This second stage is only 15 generation, so it means in total 3,000 case instead of 4,000. So we have reduced the total number of calculation by 1,000, and we also have more optimization, which is, let's say, converging quicker because all solutions are near the Pareto front. So maybe if we also run something like 20 generation at second stage, maybe we will get more feasible solution, but the goal isn't here to get more feasible solution, but update more quicker the Pareto front to speed up the convergence of the optimization. So this was by using a finite element calculation, okay? However, you know that finite element calculation is maybe a bit long, so some other techniques could be used. For example, we now are going to use this genetic algorithm using equivalent circuit model, and also there are some issues. We are going to use also experimental design method using FEA model. The advantage of this is that calculation amount is smallest because it's a kind of sensibility analysis. We can have also high model details because it's based on FEA calculation in behind, and we can take into account all objective function. The disadvantage of the equivalent circuit model is that the model detail is low because it's equivalent model. Objective function also is limited. We cannot check all, or we cannot implement all objective function like torque ripple. The advantage, of course, is that the calculation time is very quick. So as I already said, with the equivalent circuit, we can investigate high speed, low speed, but torque ripple, voltage harmonic, stress, and demagnetization cannot take into account. So what we are going to do is use those new techniques for the first stage only. Second stage will still be the 15 generation, 200 cases using full finite element solver. Okay, and now we are going to see this equivalent circuit model, okay? And firstly, we will just focus on maximizing torque at both low and high speed. Okay, that will be our only objective function. Okay, and by doing that, you can see that we've got 0 feasible solution. Okay, using this equivalent circuit model. So the next step will be adding some constraint like iron loss, voltage, and volume. In that case, we can reach some few objective functions here. Some few feasible solutions. Only 4 points are in the feasible area after the second stage optimization, and that's maybe could explain because in that picture here you can see the magnet width, one of the constraints. Okay, and you can see the calculation performed with the equivalent model in blue, and in red was the previous one, full finite element for both first stage, for the first stage for both. And you can see that using the equivalent circuit model here, you can see that we are now narrowing down the range, but as the circuit equivalent model is not able to consider all constraints, we are going to use this range for the second stage, but this range is not adequate because it's missing some information, and this range has converged to some values which is not adequate. For example, here the magnet width will be too high and will not be able to be below 13 millimeter here in the second stage, and maybe for the high speed calculation it will not be good. So that's why we have very few feasible solution, because in fact in the first stage the narrowing down is not performed correctly because some constraints are missing and some model details are missing. The next one will be narrowing down using this experimental method design. So I will make it shorter. It's based on some gauche techniques, and it's more or less some sensitivity analysis. This is based on sensitivity calculation. Okay, and the good point is that you can use full finite element solver and behind, and you've got much less calculation to be done. The disadvantage is that the sensitivity for one variable could be completely different and also invert the depending of some objective functions. Let's take an example of this variable, still the LM. If you remember this variable, that's the distance between the magnet and the border of the rotor. And now we are checking the sensitivity of this variable. So here is this variable. We are checking the sensitivity of these variables regarding the torque ripple at high speed and the average torque at high speed. And indeed, you can see that when you are here at, let's say, small value for the LM, the torque ripple is increasing. But also, when we are at small value of the LM, the average torque is also increasing. So it means that if we would like to maximize torque, we will have to be maybe here in that range. Maybe I can make a small drawing here. So we need to be here in that region. So it means also here in that case, and it means that now we are not going to reduce the torque ripple but increase the torque ripple. So it means we have to prioritize, and no single decision could be made. And here again, narrowing down process is a bit critical, and depending on the prioritized objective functions. Let's have a look, for example, if you prioritize iron loss minimization at high speed. So prioritize minimum loss at high speed means that here you see the loss, right? Okay, and here you can see that we need to select only this range here this range for all the variables. And then after the second stage, you see that we get some solutions that are here completely outside of the feasible solution. So this is also not good. Let's take another examples by now prioritizing high torque at sensitivity, high torque at high speed. So you can recognize this picture, which is the same as the one I showed previously here. Okay, so now we will focus on this here, that region, because you see that torque is high. Okay, so we will reduce the range like it's in red highlighted here. And now you see that using this, we have 3 points in the feasible area. So here also we can get some points, but it's not easy doing that. Here is the cost calculation, okay, and the summary table, which is summarizing everything. So here you've got the initial one. So this one is first stage only. I mean, one single stage only. Okay, so it's the first slide I presented, 200 cases, 20 generation, so 4,000 cases in total. Okay, here we've got in total 5 generation plus 10, so 3,000 in total. Okay, and we've got a nice amount of solution. And then here comes the 2 other method we have seen, and you see that we are depending on the narrowing. We could have 3 or 0 or 4 or 0, so it's really not easy using those methods. Using full finite element calculation will be, I think, the best one, and we can get a nice amount of feasible solution in the correct area. We also have significantly reduced the number of cases and the calculation time. So as a summary, yeah, indeed, using equivalent circuit, maybe you can excessively narrowing down, and so no solution. With the experimental method based on sensitivity, maybe you also are not going into the correct direction, so narrowing down is not performed correctly as well. So using genetic algorithm with full finite element method at first stage and second stage, calculation cost is indeed a concern, but with some parallelization on HPC, you could achieve nice results for multi-cases in a reasonable amount of time, and you get also many solutions in the feasible area. So thank you very much for listening. Now we are going to the part number 2. We will maybe go into more details and case study, and we will talk about topological optimization, which is also a bit different.
Yes, thank you very much, Yves. I mean, with your first part of presentation, actually you made my life much easier than I was expecting. So then I can directly jump into the case studies. I think you see my screen very fine, and you can hear me, and you can hopefully see me as well.
Yes.
Great. Okay, so following the case study and the basic methodology that was presented by Yves, I will start with 2 case studies that are still using this parametrics kind of optimization, still using the genetic algorithm. And then after that, I will show you a case study which moves a little bit from the parametric optimization, and it will go more toward topology optimization. In this case study, we focus on the NVH aspect of electrical machines. To give you just a little bit of background, I mean, on the design process that we go through here. Basically, what we are trying to do with this design process is to find the right balance between performance, efficiency of our product, which influence the range of our vehicles, the cost, and a parameter that is getting more and more important is the sustainability. So if we just focus today on like sustainability, basically we have some specific part and components in the electrical machine that has more negative impact on the sustainability of our product. One parameter that we use to compare different elements used in electrical machine is actually ELU, which stands for environmental load unit. Looking at this table that I have on the left, we will see the top basically 5 are somehow used in the magnets. So we can say from this table that magnets are like the least sustainable basically elements. And then after that is copper. And the rest, for example, iron, like steel used in steel lamination, and also the aluminum, they have much less impact. So that's why here in this presentation, I'm gonna show you 2 case studies that we made, and we made the design basically. In the first case study, we tried to reduce the amount of the rare earths parent magnets, and in the second case, we try to replace the copper hairpin with aluminum hairpin to again increase this or improve the sustainability of our product. Whatever I'm presenting in this webinar, we will have like 3 basically papers behind them. 2 of them are already published. It was published sometime end of the last year in IECON, and the other one will be published in 3-4 months. So let's start from the one that we have for the reducing the amount of the rare earth magnets. Let me show you a little bit of the process we go through. So our whole design process basically is made in JMAC, but we use different JMAC products for different reasons. So normally we start with kind of initial dimensioning of the motor, and that's normally done in Express, but that's not the only application of Express. We use also Express to start or to have an start point for making the template, the design template that we want. So basically we will get the design template, which is normally fully parameterized. We will from Express, and then we will put it in JMAC, and then we will further customize it for the kind of optimization that we are gonna run. This further customization can be to fix some parameter, or it can, like most of the time, increase the number of parameters that we would like to vary during the optimization process. Then, of course, we get the parameters that we want to have as constraint, as objectives, and then we will list our objective. We will run the optimization based on genetic algorithm, and then we will make the Pareto front and the process that was very well shown by Yves. So let's look at the first case, the case that we are trying to reduce the amount of rare earth magnets or rare earth elements in the magnets. So the rotor topology that normally it is used for reducing the amount of magnet and replacing at least part of the rare earth magnet with like, for example, ferrite can be, there has been a lot of development on magnets without or with minimum amount of rare earth elements. You can, but here for simplicity, we just go for something that is well known, which is ferrite. And this double layer U shape topology of the rotor allows us to have different magnet types in the center, on the sides, and that is gonna helpful. And if you compare it, for example, with the V shape, 1 layer, 2 layer, if you make them different, then it will make kind of unbalance between the flux on the 2 sides of the basically pole, and that's gonna be problematic for you. So this rotor topology basically fits very well when we try to reduce the amount of the rare earth magnet in our design. And then you will see that during the optimization, we will focus more on meeting the performance requirement at high torque, basically. And then we have like the efficiency points that are more towards like lower torque and mid-range speed, as you can see in the graph on the bottom here, that shows kind of real operation of the electrical machine inside the vehicle. That you can see it rarely goes to the peak performance. So that's this region basically shows where we should do the optimization toward efficiency. As I said, we will start with the parameterization and making the template in the way that basically we want. And that shows the figure on the left shows like the start point that we had for this optimization work. Then we set the objectives as mentioned by Eve, but one very important factor here is how we weight different targets. So as you can see here, we have the first objective, which is to reduce the amount of the rarest magnets. We are not putting any requirements on the freight, for example, at this case. And then in the second one, of course, we would like to meet the performance requirement in terms of the torque. We would like to have some level of demagnetization ratio that can be allowed on the electrical machine. We would like to minimize the amount of the torque ripple, and we would like to maybe have as compact as possible motor. So this is not really the full list. Normally we work with a much higher number of objectives, but this is kind of representative, I would say, for this case. If I want to increase it more, it can be complicated, and then it will be a little bit harder to follow up. So this is an example. So we run the optimization here. This is an optimization with something like 1150 cases. And as you can see, the amount of the magnet has been reduced and stabilized after like the case of almost 800. And then we have the demagnetization ratio, which has increased to like 97.5%. And we could meet the torque requirement, as you could see in the previous slide. It is set at about 400 Newton meter. And then you can see how different is now the design. Thinner like layer on the side for the inner magnet, thicker on the outer ones, maybe to reduce the amount of demagnetization ratio. And then you have the amount of the magnet in the center, which are red here, representing the rarest magnet, has been as well minimized. That was one case study. The other case study, this one will be actually published in ICM 2022 in a few months. But in this case, we had the same rotor topology as you could see in the previous case, double layer U-shape, but we are trying now to replace the hairpin, basically copper hairpin, with aluminum hairpin to also improve the sustainability of our product by reducing the amount of copper or minimizing the amount of copper or totally remove it basically from our design. We do the same process. We parameterize it in the way that we want. We put the objective. The objective, of course, will be different here because here it is very important for us to still reduce or keep the amount of the current density in the slot, like minimize from some levels, because we know if you have the same level of current density in the slot in the aluminum hairpin as you have in the copper hairpin, you are going to produce much more losses. So that's why we need to control the current density. Then we try to minimize the total losses, which is the sum of the joule and iron losses. We would like to meet the voltage requirement based on the state of the charge of the battery, for example, and the level of the power that we want to get. And we would like to meet the torque requirement, and we want to minimize the amount of magnetic gain at the same time as replacing the copper hairpin with the aluminum hairpin. You can see the same process optimization is run. In this case, we ran it. We didn't really need it to run for very high number of cases. This case shows something like 350 cases, much less than the case I mentioned before. And then we made the Pareto basically curve, and then we tried to find the most optimum design that we felt more comfortable with. We could get the design that we want. So normally after this optimization, you run some more smaller optimization with lower number of cases to further optimize with a smaller range of the constraint. But that normally shows what you see here, basically the design that has been achieved in this case. And then this will be a study on the system level together with the amount of the current, for example, that you need for the design to get like the sustainability and ELU picture of the whole system. In this case, it may not be very successful because, as you can see, the amount of the magnet was increased, and that actually killed a lot of benefits that we had by reducing the amount of the copper. But in terms of the optimization, it went pretty fine. Now, these were all still on the parametric optimization level. Now I'm gonna show you a case that we do. Basically, we move from parametric optimization to like topology optimization. And normally that's the process we use when we go deep into detailed design of the motor, when the concept is finalized and now we are gonna do the detailed design of the machine. When it comes to detailed design, then you need to fix all the barriers because we know like small changes in the barriers will influence the tooth forces, for example, in the stator, and that will generate noises in the machine. So in this specific case, we didn't have so much possibility to redesign the whole machine, but with minimum possible changes, we wanted to improve the NVH and the level of the noise in the electrical machine. And the reason basically in this case was that because the electrical machine was already on the vehicle and we didn't have the possibility to redesign everything. So just a little bit of background on topology optimization. I mean, what does it really do? This topology optimization is used when you have really difficulty to make the parameterization. I mean, imagine you want to make like optimize one barrier, for example, in the whole design. I mean, depending on what kind of parameterization of that model you have, you will still limit some design possibility. So that's why instead of doing like selecting some part, fully parameterize it and let it run in the optimization process, in this topology optimization, we just select the area that we want to optimize. And then we will let the software to give us ideas on the best possible design for that barrier. And the way that the software works basically is that for that specific area, it will pick up elements, and with some level of the resolution, it will exchange the material with the air for different combination, and it tries to find the most optimum shape of the barrier. This is the case study that we had. As I mentioned, we wanted to keep the same rotor stator lamination because maybe the tooling was ordered. I mean, it's quite interesting case. And the only possibility that we found actually to improve the NVH and the level of the noise in the machine was to change the shape of this central barrier, as you can see here. This is the original shape of the central barrier. So when we did the detailed analysis of the noise from the machine, what we learned was that what is really generating the noise and the order of the tooth force that is originating that higher noise is coming from the order 48. And we know this is an 8-pole machine with 48 slots. So order 48 plays quite important role here. So what we did basically was that we needed to set some kind of objective and constraints around this optimization. As I said, the motor was already produced, it was already on the vehicle, so we couldn't basically change the performance so much, so we limit the change in the performance to maximum 1%. Then in the second objective, we wanted to minimize the value of the 48 order harmonic on the tooth force. At the same time, by reducing the value for order 48, we didn't want to compromise on the other orders as well. So we wanted to have the sum of all the important orders, which can be 8, 24, 48, and 56 to be still minimized as well. And then we wanted to have the same control. So we didn't want to run the motor with different ID and IQ, for example, and you know how much that control influences the NVH. So putting that into topology optimization, actually we got pretty fantastic results. You can see the shape of the barrier in the center, it changed from something like this to this. We made some more changes, so this shape is not really final, but that shows basically the concept. And using just this small change, just doing topology optimization in that very small area, we could reduce the order 48 by 50%. In the radial direction. In tangential direction, it was like 30% reduction. And that actually reduced the whole noise imitated from the machine by something like 3 decibels, 3 to 4 decibels. And that was good achievement with very small change in the production, a very small change in the motor design, the same level of the efficiency, the same level of the torque, a small reduction in torque, maybe less than 1%. You could still gain quite a lot with this methodology, basically. And you can see also here the differences. So the dashed one here shows the level of the tooth forces after doing this topology optimization, which correspond to this updated design. And you can see how much the level has been reduced. And that was the speed range that we had issues. It was between 2000 RPM to about 3500 maybe RPM. So that's where we wanted to improve and reduce the level of the tooth forces. And of course, another very interesting thing was that our calculation actually and the whole design process and the evaluation process that we had was very much matching our measurement results. So not only for comparison it was representative, but also the absolute value was quite well estimated. So that was quite good sign for us, and that made changes in our design. And this is actually something that is already implemented in one of the most sold electric cars within our group. When I'm referring to the group, I'm referring to the Geely group. This was not specifically done for Polestar, but for Volvo cars. Yes, thank you for your attention.